Okay, so in the last lecture we learned about the real-time transport protocol that is used to encapsulate media data, and the session initiation protocol, which is commonly used for the call management functions, right? So now we are looking at not the application layer protocols, not how the applications can encapsulate media, but now we are looking towards the network, and let's see how can we configure the underlying network, that is the routers and switches in the internet, to help us with the media delivery, to help us deliver the right quality of service for all these kinds of media applications. So now instead of looking at these application layer techniques such as some of the ones we learned, the prefetching and buffering for video, estimating the playout delay, adaptive playout delay, and setting it so that we do not use so many packets, adapting media quality to the bandwidth. So instead of all these techniques, now we are looking at how the network can be configured to support media applications. So there are three approaches we can take. First of all is the first line here. It's doing nothing, basically letting network handle based on the best effort service. So that is making the best of best effort service. You just deploy sufficient infrastructure with high enough rate networks and let them handle with the packet switching based on first in, first out type of routers. Some of the packets will be lost, yes, but well, in fact, most of the internet today is configured this way. There is no underlying network mechanism to support different media applications. But if you want to build support, we are building complexity at the edge, at the application layer, at the edge devices, at the CDN levels. So that is all at the edge of the network, not at the core of the network. So this first row, let's also show this ink markup. Yeah. So this is the most common approach today we take in most of the internet. We treat all traffic equal, be it media or your web browsing. There is no guarantee provided by the network itself. Yes, your application layer, your applications can provide some guarantees, but not the network. So all the support is at the application layer level, such as using CDNs, overlays. Perhaps you can do some network level resource provisioning. You can allocate resources based on demand, such as in the case of CDN, right? We our DNS can let the CDNs with the less amount of traffic to send data to the requesting clients. And this has minimal complexity, so you can really do it. It's deployed everywhere. But what we are looking today mostly is providing differentiated service for different kinds of applications. The second row here, differentiated service. Here we can provide some soft guarantees. This is not to say if you are running a video streaming application, you'll be guaranteed to have, let's say, 5 megabits per second rate. Or it's not like saying if you're running a voice over IP application, you're guaranteed to have 100 milliseconds delay at most. No. This is simply helping you to get these kinds of quality of service requirements, quality of service benchmarks, but the guarantee is still soft. So it has some complexity. We will see methods of this. And it is in fact deployed to some degree. And in the last line, we have per connection quality of service guarantees. So this is very much like circuit switching, how telephony networks are configured today. Once you establish a call, you are allocated that bandwidth and you are guaranteed to have that bandwidth throughout your session. And this is almost non-existent in today's internet because it has a lot of complications. So in the telephony networks, maybe there were not many routers, only the switching centers, and you allocate resources there. But with today's internet, you have so many networks, so many routers, so many management domains. And if you're establishing a session between two parties, if these parties are far enough, it is very difficult to let all the routers and switches in between know that a channel is established. You have to allocate resources for the traffic between these two clients, or a client and a host. It is very difficult to achieve. So there is almost no deployment as of today. So this is dimensioning best effort network. So this is the approach we have seen so far. We just throw money at the problem. We deploy enough link capacity so that congestion doesn't occur. Even if it occurs, still our multimedia applications can be mostly supported. And in fact, we have sufficient evidence that this works. So even though we do not have network layer mechanisms, in today's internet, we mostly get our media with sufficient quality, right? I do not usually experience disruptions in my voice over IP calls, or I do not experience disruptions when I stream video on YouTube or Netflix. Only time I get my things interrupted or disrupted is when I have bad end link capacity. That is the access link between my device and perhaps the Wi-Fi router nearby or the base station nearby. But once it goes to the wired network infrastructure, the fiber optic infrastructure, it's all fine. So this can work. But there are still certain challenges. What if, you do not know how much bandwidth is enough, first of all. And what if there are peak uses? Let's say there's a certain live event, and everybody wants to stream that. So this is hard to estimate traffic demand per location and also over time. Over time, there can be peaks and low utilizations. So this problem is called network dimensioning and provisioning. So it's the design problem of how to build the network topology, that is, where do you place routers, switches, and the links connecting them, how to connect them, and with what capacity to assign to each link to achieve sufficient quality of service for all users. Still, even if we do not configure our networks, even if we do not have mechanisms, throwing money in itself is a problem, and you may run out of money. That's another constraint. So, thus far, we discussed making the best effort service, correct? It's a one-size-fits-all type of service model. And the next, this corresponds to the second row in the table I showed, this table. Next is assigning multiple, not assigning, but it's partitioning the traffic into classes and having different network mechanisms or having different priorities for each type of class, each class. So you can think of this like a VIP service, or in the case of aircraft boarding, it can be a business class versus economy class. Some kinds of traffic can be prioritized. For instance, if you are having a voice over IP call, perhaps that can be prioritized over web browsing, which has almost no urgency. So then my question to you is, if you want to achieve this, I keep telling you that, and I probably also learned in the previous lectures with Professor Biplab, that these routers and switches do not have application layer protocols or even transport layer protocols, right? They only run network layer protocols. They can read network layer segments, datagrams. So, the network layer segments. So how can they understand our application data to cater to the requirements of our application? That's the question. How can we configure our networks if our routers cannot understand the type of media in the first place? Any guesses? Well, we have a hint here. It's TOS field. It's a type of service field. Let's write it. So it's a field in the IP header in the network layer. And applications can indicate these TOS field based on their priorities and requirements. If they require, for instance, low delay or high throughput or high reliability, they can indicate that in the TOS field. And it depends on the type of media they are carrying, type of application they are catering to. So with this field, now our routers can read, at least get an idea of what priorities should be given to that packet so that they can perhaps queue it accordingly or assign different weights or prioritize them and so on. Any questions so far? All right. So now let's see an example. And from there on, using the same example, we'll be driving some insights as to what kind of mechanisms should we have in the network layer. So let's say we have 4 hosts, and host 1 is communicating with host 3, and host 2 is communicating with host 4. But overall, between these hosts, this link has limited capacity of 1.5 megabits per second. And therefore, the packets from host 1 and host 2 will have to be queued and buffered in the same R1 router, because the R1 router is serving them both. Like so. Now let's further assume that the host 1 and host 3, anyway, these 2 guys are running a voice over IP application. And this application requires an uninterrupted 1 megabits per second throughput. Otherwise, they will not understand each other. The application doesn't work, let's say simply. And these guys, one of them being client, one of them being the host, the client is sending HTTP requests and downloading some web objects from the server. So this can typically happen in the internet. The same router can serve both a client-server HTTP application and a voice over IP application. So ideally, we want to give priority to the voice over IP application, right? Because probably the web browsing does not have any urgency. So perhaps, given HTTP web browsing application does not have time constraints, our intuition might be to give strict priority to the voice over IP application. So perhaps, I can always let out the voice over IP packets first. So I take this one out first, this one out second, and then I take out these red packets from the HTTP. So this brings us to the first principle here. We need to mark packets, such as using the TOS field, type of service field. We need to mark the packets for the router to distinguish between different classes, and a router policy to treat packets accordingly. Again, we are not saying how should we set the policy, but at least we should give priority to the voice over IP application. But then there is another problem. So if we always give priority to the voice over IP application, then that application can misbehave. Yes, we know that at least 1 megabits per second should be given to that, But what if that application says, I know that link is 1.5, so, let's just request 1.5 megabits per second. I just want to use all the resources. So we need a certain policing mechanism. We should force the source to adhere to the bandwidth allocations and typical requirements by certain applications. So we need to mark the packets, yes. We also need to police. If some guys are going too fast, the traffic police catches them, right? So we need certain kinds of policing. So just because you have priority doesn't mean you can utilize all the resources. So we still need to provide, this brings us to the second principle, some isolation for one class from others. So perhaps, how can we do it? Well, yes, we give priority to the voice over IP, but still we isolate the other application a little bit so that even if the voice over IP application overreaches and uses up more bandwidth, we still ensure some capacity, some throughput for other applications. So one other way we can do this is, well, we can just assign fixed, non-shareable bandwidth to each flow, just like circuit switching. Once that voice over IP application is declared, we just allocate perhaps 1 megabit per second, because we know voice over IP can be well supported at 1 megabit per second. So no matter how it requests, we always assign that much. And we strictly give out the rest, the 0.5, to the HTTP application. But it causes other problems. So what if that voice over IP application is only intermittent? It's not continuous. And even if it is continuous, there are talk spurts, and there are also silent periods. And in these silent periods, we learned that we are not sending sound chunks. We are not sending any packets, or very little amount of packets. So we could actually opportunistically use these silent periods, but we are not making use of them. And we also know that in a web browsing application, this much 0.5 megabit per second requirement is not usually constant, because only when you request objects, something is downloaded. So this brings us to the third principle, and it says, while providing the isolation, it is desirable to use resources as efficiently as possible. So now with these insights, let's repeat them again. First, we need to distinguish packets by means of marking them. Second, we need to provide some isolation. And third, even if we give isolation, we want to use resources as efficiently as possible. So with these principles, now we will think about what kind of scheduling and policing mechanisms we can have. A little bit of terminology. So scheduling is the act of choosing the next packet to send on the link. So you can have a scheduling algorithm, for instance, and it decides using the algorithm, a certain algorithm, certain rule, it decides on what packet to push to the link first. Perhaps you want to push the voice over IP application packet first, but under which constraints, using what kind of policing? Now we're going to discuss those. So typically, if we are talking about the best effort service, that is most of the routers in the IP networks, they are using FIFO, first in, first out scheduling. So it's just like any queue. The first person that comes into the queue gets served first, and the second one that comes gets served second, and the last one that comes gets served the last. So typically, this is what happens in the case of packets in the routers. But there is also, in addition to that scheduling policy, there is also a discard policy. Well, this can be a part of the scheduling policy also. Well, these routers do not have unlimited memory. They have limited space for incoming packets. They can only take this much. So what happens if after the buffer is full with packets, a new packet arrives? Are you going to drop the one that arrives the last? Are you going to drop the packet that came first, which in this case is this one? Or are you going to randomly choose a packet to drop? Okay, so you can, or you can, you can just drop based on priority. So as we know, certain applications can tolerate loss and certain applications cannot tolerate loss. So perhaps we can drop the packets from a tolerant application, an application which can tolerate some loss. So all these policies are possible in routers. You just need to write certain algorithms there. So let's go over them one by one. And in doing so, we will be looking at more advanced scheduling and policing mechanisms. So first is, well, of course, other than the first in, first out scheduling, the first smarter scheduling policy is the priority queue. So this is also a data structure, priority queue. Just like that, just like the priority queue, we have priority scheduling. So we have multiple classes, perhaps based on the type of service field, and we are always prioritizing a certain class of application over another. Let's see here that example. So let's say I have red class and green class. So first, so this is the arrival. These are the arrivals. And the rectangular ones are the departures. So because my queue is empty, my buffer is empty at first, whenever that red one arrived, which is the higher priority, I immediately served it and pushed it to the link. Then a second class and third, the second and third packet arrived. Second is green, third is red. So if this was a first in, first out scheduler, what would I do? I should serve the second one first, correct? Because that came first. But now because the red class has higher priority, I'm serving the third one next, and then I'm serving the second one, the green one. And let's say a fourth one arrived later on, then I serve the fourth one because my buffer is empty. And if a green one arrives when the buffer is empty, of course I can immediately serve it. Yeah, so it's very simple. I just always look if there is a high priority class first. Then if there is, I serve it. Otherwise, I look at the second priority, third priority. I don't need to have just two classes. I can have multiple classes here. So let's think about some real-world examples of this. So in real life, outside of networks, for instance, we have hospitals and the university health center here operating this way. So if an emergency case arises that always have higher priority, I mean, if some guy is getting a heart attack, you cannot say, but I came first. You should serve me first. They will have priority queues there. And yeah, in fact, if you read some signs there, they will say that the queue numbers are not necessarily called in the order. So that is another indication of their priority queues. Okay, so the second is the round-robin scheduling. Here we have, again, multiple classes, and we do this for fairness for all the classes. So let's say in my router's case, some application is starving me out of resources, starving me out of bandwidth resources, and I always have to, and I'm always requested to serve that kind of application, although that probably doesn't have much of priority. Then round-robin scheduling may be an option. So here again I have multiple classes, and I serve someone from this class, someone from the second class, someone from the third class, and then I go back. I again serve someone from this class, someone from this class, and someone from this class. So by round-robin fashion, I go back and forth, I make cycles, and repeat. So this avoids starvation of any class of application due to demand from another class. And if you look at the same example here, so the red one came first, another red one, and another green one, right? So if I had a FIFO scheduler, I should serve the second one after the first one, because the second one came before the third one. But in the round-robin's case, because I serve the red class here, then I should look if I have a green class waiting. And yes, I have the third packet, which is green, so I need to serve it next. And then I need to serve a red one again. Of course, here, I served two red classes subsequently. Why? Because I didn't have any green class packet waiting. Let's think about real-world examples. Anybody has an idea of round-robin scheduling in real life? Well, I think one example could be the scheduling in the processors, in the central processing unit, CPUs of computers. So in your computer, you have perhaps a few processors or a few threads, yes, but you have many processes running. And your CPU needs to scan the processes one by one and cycle over them in a round-robin fashion. So that's one example of round-robin scheduling. So now, round-robin scheduling is fixed in the way that it always serves one packet from one class and then another one packet from another class and so on. But can we generalize this to give priority for a certain class while still ensuring some throughput for the other classes? And the answer is weighted fair queuing, WFQ. So you can think of this as generalized round-robin. But it differs from round-robin in the sense that each class may receive a differential amount of service in any interval of time. So let's say we have three types of applications here, three classes of applications here, and I'm assigning each of them a weight, W1, W2, and W3. And obviously, this link is limited. Let's say this is R. And then for type 1 class application, my rate is going to be W1 over W1 plus W2 plus W3 times R. So I assigned W1 out of the total weight portion of the available bandwidth to type 1. Well, if we generalize this, what is the rate or throughput for ith class? That would be, let's say Ri is that. Ri would be Wi over all right. I'm going to write it a little higher. Let me write it here. Ri equals Wi over the sum of all W's times R. So this gives the per link rate, per class rate of class I. Any real world example you can think of here? well, I couldn't come up with a great example here, but perhaps for different departments of a company or in an enterprise, a large corporation, you might have different priorities, right? So let's say you are all using the same mainframe or the same cloud service, but perhaps you can prioritize the finance department over a marketing department, let's say, or a human resources department, because you need to pay your debts first, because you need to calculate your taxes first. Maybe that has a higher priority. So you can assign more weight to that. Any questions so far? Okay. So now let's start with the policing mechanisms. So far we discussed the scheduling mechanisms, but policing was one of our earlier insights to regulate the rate at which each application class is allowed to push packets to the link. Because if we do not implement policing, some applications may starve others out of resources just because they are given the priorities. But what aspects of the rate should be policed? So just when I say, okay, you're going to have 1 megabits per second, is that the average rate over your whole day, or is that the maximum rate you can achieve in every second? It depends a lot. Why? Just to give an example, so 100 packets per second is the same as 6,000 packets per minute in terms of the average packet rate. But imposing both requirements might have different implications. So for instance, we know that for the video streaming application, long-term rate is the most important thing because we can buffer some data. But for certain applications, let's say for browsing web and downloading an image, your burst rate is more important because you're only clicking one picture at a time, and then you're waiting a few seconds to click on the next one. So in fact, we might want to regulate both the average rate, the long-term average rate, and the peak rate. Because if some applications take up all the peak rate, let's say they are sending burst packets into the link, then my other application, which requires steady throughput, such as voice over IP, might get affected. So I want to regulate both the average rate and the burst rate. And one way to do this is to use a leaky bucket. Now, you might be thinking, what's the relation? It's just an abstraction of policing mechanism for policing both the burst rate and the average rate. Obviously, there is no actual leaky bucket in the routers. It's all virtualized in software. But this is a good abstraction to understand that. But before that, let me give an analogy first. So you have been to museums before. Now let's think of a museum that only takes guided tours. So for every person that is visiting that museum, there have to be one guide accompanying that person. And I can only have a certain amount of guides in the morning. So let's say in the morning, 9 a.m., my museum opens, and I have a pool of guides here. Let's say that their maximum number is fixed. And the customers are arriving to the museum. But the customers are not arriving at a constant rate. They arrive at random intervals, just like packets. Sometimes they arrive individually, one by one, very slowly. But sometimes a large tour group arrives, So I have to serve all of them individually by my guides. So what happens is whenever someone comes to the museum, that customer takes one of my guides and then they leave. Let's say then 3 other people arrive, they take 3 of my guides and then they leave. But I need to replenish my guides, so I also have a constant rate of incoming guides. So let's say in every 5 minutes, I have a new guide arriving. Of course, unless my number of guides reaches the capacity. I can only keep so many guides. So this is very much like how Leaky Bucket works. Now, let's think of guides as the tokens, and my museum is the bucket. It can only hold so many of these guides, which are tokens, and the customers are the packets. So packets arrive. These are incoming packets. And I have my guides ready waiting. So these are all the guides. And I have only B amount of tokens at most. That is my capacity of tokens. And if my bucket holds less than B tokens, I have my incoming tokens, R tokens per second. Every second, R new tokens arrive. And with each packet, I remove one token, and together, I push them to the network. One token per packet. One token per packet. So when you think about it then, it regulates both the average rate of packets I can push to the network, and also it regulates the burst rate of packets I can push to the network. Why is that? Well, first of all, over the long run, I can only serve R packets per second, because eventually, if so many packets arrive, my bucket will be emptied, right? I will have no tokens in the bucket eventually, just like my guides will be all consumed if too many customers arrive. And I only get R tokens per second, which will be equivalent to the number of packets I serve, which will be equivalent to the rate of packets I serve. That I can serve only R packets per second in the long run. So my average rate threshold is R packets per second, just R. And I also have a peak rate. Instantaneously I can serve more than R packets per second. Why? Because in the best case, I have a full bucket of tokens, which are B tokens, and I can immediately serve B packets if they arrive. That is assuming my bucket is full. Let's say they're coming in the morning, 9 a.m. All B customers are coming to my museum. They can use up all my guides here. So now, if you look at the number of packets admitted, it can be, well, I can admit, if you look at the number of packets admitted over an interval of t, an interval of length t, in the best case, first of all, I serve all the B packets, right? If my bucket is full, I can serve all the B packets first, and then over a time of t, because the tokens to the bucket are arriving at R tokens per second, I can also serve R times t number of packets. So this gives me the total amount of packets I can admit over a time interval of t, RT plus B. Any questions on this? So we will be building on this and weighted fair queuing in the next. So it is very important that you understand this now. It's a kind of a weird concept to think about this in this abstraction. Obviously, there is no actual bucket in the network. There is no token arriving or anything like that, but they are basically all implemented in algorithms. So perhaps there is a counter, and that counter increases every second by r, and that counter, when it reaches a threshold, it stops, and whenever a packet arrives, it decrements the counter. Perhaps that is the way to implement this algorithm. Any questions? Okay, so I assume it's all good here. So now this is how we combine our scheduling and policing mechanisms to provide some soft quality of service requirements, some soft quality of service guarantees. So if we combine these leaker buckets with the weighted fair queuing, so here's my bucket, and here's my weighted fair queuing. Notice how the queue is on the right side of the router. Bucket is on the left side of the router, that is before the router. I can guarantee the maximum delay a packet will experience while waiting for service in the queue. That is after passing through the leaker bucket and the router. Okay, so that is the time it waits in here while waiting in this weighted fair queue, or it's in here. So this is how it works. Again, let's say I have two classes of traffic, right? That is W1 or let's say I have n classes of traffic, okay? I'm assigning them each W1, W2 to Wn weights in the weighted fair queues. And they might have different leaker buckets with the different bucket sizes, B1 to Bn, and each bucket might have different arrival rates, R1 to Rn. So now let's find out the maximum delay a packet will experience while in the queue. So let's assume that in the worst case scenario, a B1 number of packets will arrive to the leaker bucket, and our packet, in the worst case, is the last one of these B1s. So all of them will be passed into the queue, right? So I'm assuming, to calculate the worst case, my bucket is full, and I'm measuring the delay for the last one of these B1 packets for the bucket 1. So immediately B1 number of packets are passed here because my bucket holds B1 tokens, and I'm measuring it for the last one of these. So what was my rate in the weighted fair queue for a class? Well, it was W1 over the sum of all the other weights times R, correct? And I need to serve B1 packets at this rate. So if I divide B1 with this rate, this gives me the time, or the maximum possible delay a packet will experience in the queue, which after some manipulation is equivalent to this. This is, I assume, the weight 1, so that is 1. Right? So what I did is I'm looking at the last one of these B1 packets because I'm calculating the worst case delay. And I'm also assuming my bucket is full, so all of them are passed to the queue, and I'm calculating the time spent in the router's queue, in the weighted fair queue. So to serve B1 packets at a certain rate, I divide the number of packets to my rate to find the delay experienced. Any questions here? Okay. So we have seen the differentiated service by implementing certain network mechanisms for different kinds of traffic, for scheduling and the policing mechanisms for different kinds of traffic. And they can, although they do not provide a lot of guarantees, they can be still used to ensure soft guarantees for my multimedia applications. But then the question is, can we provide hard guarantees, full guarantees to different kinds of applications using IP networks? Can the network actually guarantee that ongoing flow in a high priority traffic will be serviced with based on the quality of service requirements for the whole service duration? And the answer is, it cannot be supported. Yes, we can build per connection quality of service guarantees so that each source destination flow is treated differently and they are guaranteed something. But eventually we are limited by our infrastructure. How much throughput we built into the network is going to limit my guarantees. So now we will see why other network mechanisms and protocols are required when a per connection service guarantee is needed in the last one of these. So yeah, as I said, the basic fact is that we cannot support traffic demands beyond the link capacity. So for instance, if two applications, both of our running voice over IP applications, require 1 megabit per second link, and your link capacity is 1.5 megabits per second, well, you can have two choices perhaps. You can just give out the best effort service and let both of them waste their resources. Or you can just block one of them. But so the traditional telephony network is an example of that blocking, right? Once the call is admitted, they are guaranteed to use that service for the duration of the call. And similarly, in our case, there is no point in allowing a flow if it's not going to receive the required quality of service. So by allowing or blocking the flow based on the requirements here, we can perhaps guarantee at least one of them will get their service. So this brings us to the fourth principle. Here the flow declares the needs. The network may block if it cannot meet the needs. So by providing guarantees here, we do not mean everyone's request will be guaranteed. Everyone, regardless of what kind of quality of service they require, it will be guaranteed. We don't mean that. But what we mean by guarantee is that after the session is established, or after the call is admitted, or after the application requests and gets the resources approved by the network, then that is a guarantee that it will be given the sufficient QoS. It will be ensured of the sufficient QoS. That's what I mean. And the only way to guarantee is to allocate the resources to the flow. So this is known as resource reservation. So we can have we can set up the calls, and then we can signal to all the routers using certain reservation mechanisms. We can declare our traffic needs. We can declare our quality of service needs. And for each link and for every single router in between, we have we need to have reservations and allocations of certain throughput and delay guarantees. So if, let's say, this client here is communicating to this server, they have to reserve that resources from the whole network in between. So all the links, all the routers here need to allocate them the resources. And this is very, very hard because it goes through a lot of routers. And for every single packet, now you are allocating, now you are reserving. Maybe a lot of them will be able to reserve that, but maybe one router is too congested that it cannot reserve that. So are you going to have to wait for that, or are you going to try another route? What if the other route also doesn't work? And what if everybody wants to do this? It's not just these two clients, perhaps, but then now that you can get it guaranteed, everyone wants to do this. So it is very, very difficult. But a lot of research and development is ongoing, not in providing these end-to-end quality of service guarantees, but in building good, efficient scheduling and policing mechanisms into today's networks. So probably this is not going to be there for most of the applications, because by deploying high capacity links with fast enough links and routers, we can probably have good enough networks, good enough for most applications. So now the one other aspect we can think of is perhaps these satellite networks, right? There are many low Earth orbit constellations, and eventually they will be integrated into our IP networks, and the cellular networks, perhaps 5G, 6G, might operate with them. So they will provide alternative routes. Maybe if your existing network infrastructure, the submarine cables are congested, some routers are congested with traffic, perhaps they will provide an alternative route. So if we build sufficient infrastructure with sufficient redundancy, high availability networks can provide most of the soft guarantees, which will probably be enough for most applications. But for a small sliver of applications that require uninterrupted flow, perhaps like remote surgery application, perhaps this will be a feasible route we can take. Any questions? So this concludes our multimedia chapter. Would you like me to go over the leaky bucket or the weighted fair queuing again? Is that all clear? So in the last year's exam, there was a pretty difficult question on the leaky buckets. I think less than maybe 10% did it well. So this is not to say this year it will be the same. It will be a different question. That question is in the tutorial 5, last question. So you can check it out. So our purpose here is not memorizing these kinds of formulas. There was a couple more here. All these can be derived by logic, right? So here I am basically assigning weights to each class of traffic, and they will be served based on that rate. And in the leaky bucket, the idea is that I am filling my bucket with a certain rate, and my bucket can only hold a certain number of tokens, and the arriving packets may come at arbitrary intervals at an arbitrary rate. So this is not about using formulas to calculate anything. It's all logical. Once you understand, it all follows from there. So if you're sure, if you don't have any questions, I'm going to solve the last question of tutorial 4. Okay. So, yeah, I solved the first 3 questions, and because the last one is on wireless and mobile networks, I didn't attempt that. So, suppose the correspondent in the figure below were mobile. Sketch the additional network layer infrastructure that will be needed to route the datagram from the original mobile user to the mobile correspondent. Show the structure of the datagrams, include destination addresses of the datagrams between the original mobile user and the now mobile correspondent. Assume indirect routing, you may assign arbitrary addresses. So, okay, we have our mobile moved from this earlier permanent address, or earlier home agent domain, into this foreign agent domain, and it's been assigned a new care of address, correct? And now my correspondent is also mobile. So let's say my correspondent was earlier in its home agent's domain. So this is my home agent of my correspondent, and this home agent also assigned a permanent address to my correspondent. Let's say this is 1111 for simplicity. But now we are saying that my correspondent moved into another address, and in this new address it is in a foreign agent's domain. Right, this is my foreign agent. And here it is assigned a new address known as the care of address. And this is, let's say this is 2222. Okay, just assigning very simple addresses. Let's say this is the foreign agent of the correspondent. So, once these mobile devices move into a new domain, the first thing they do, either themselves or through their foreign agents, is to register their new care of address with their home agents, correct? And in mobility chapter, we also learned that any datagrams targeted for the permanent address of the mobile node always goes through the home agent. So if this correspondent now in this new location addresses this mobile, it sends datagrams to the home address with the permanent address in the IP header. So that is 128.119.40.186. So this is my IP header. There's some data in it. And home agent, because it now knows the COA, it tunnels this packet to the care of address. So it sends it to the foreign agent. And how it does it? It takes the earlier datagram, 119.40.186. Let's say this was my datagram, right? It encapsulates it in another datagram with the destination address as the care of address. That is 79.129.13 and 2. So this is encapsulation and tunneling. And now this packet arrives at the foreign agent. Foreign agent removes the outer layer and sends the original datagram 128.119.40.186 to the mobile node. So far, this is what we already learned in the class, nothing different. But now, this mobile node is going to address this correspondent. Let me draw that with another color, perhaps blue. Yeah. So now it doesn't know the care of address of the correspondent, but it knows the permanent address of the correspondent. So it will address these datagrams to the home address, right? So that's going to be 1111, because that's what I assigned to the permanent address. And this home agent, once this correspondent moved into new location, was registered, the new COA. So anything it has, it will send it to it will tunnel it to the foreign agent. So we have the earlier datagram, and this is encapsulated in another datagram with the destination address of 2222. This foreign agent receives it, and then in here it's going to remove the outer layer and send the original datagram to the mobile correspondent. Any questions? So this is kind of now a rectangular routing, not triangular routing, but when you think about it, it's more like a rectangle. Okay, so I don't want to start the new chapter now, but I uploaded the slides. So we are going to be studying network security for the rest of our lectures. I think we have about 5 more lectures. We're already ahead. So it's going to take me at most 4 lectures, I think. So in the remaining time, what I'm thinking is perhaps we can see some of the security applications, some popular applications. Maybe if the time permits, we can look at after looking at transport layer security, we'll be looking at modern approaches to securing industrial control systems, or perhaps look into blockchain, because these will be using some of the primitives that we will learn in the security chapter. But then I'll also do perhaps something like an office hour for the last lecture. Maybe I'll cut it short, and then I'll let you ask questions on the part that I taught. So if you have any other suggestions, I'm open. But yeah, so in the last year's lecture, it was on Zoom, so I was receiving a lot of questions, and I hardly finished on time. But this year, almost nobody is asking questions for some reason. So I very quickly taught all the slides, and we are really ahead. Any questions? If not, you can check out the security slides. I'm expecting a little bit more activity from your side in security, so please contribute. I'll be asking some questions, some ideas. It's not going to be just, this is how it's done, this is what we do. It's going to be more like an evolution of security, some historical perspective. We'll be looking at some earlier ciphers from ancient Roman times, and then towards the Second World War, and then we're going to look at modern cryptography. That is what most of our systems rely on today: the banking system, the internet, the web. Yeah, so I hope to have more activity from you. And that's all. Have a nice weekend, and see you next Wednesday.